Hi, this is S. Jamal. I welcome you on my YouTube channel, JCS Science Lab. We always observe that all the objects fall towards the earth. When we drop an object from a height, it falls towards the earth. And we also know that all the planets are revolving around the sun. All the satellites revolve around the planets. We are here settled on the earth. When we jump upwards, we fall back on the earth again. Do we know that which force is responsible for all these phenomena? Yes, that is gravitational force. Gravitation means force of attraction between two objects. The concept of gravitation was started far back. Aristotle, you must have heard Aristotle. He believed that all the objects fall towards the earth as they are searching their natural place. He also believed that heavier objects fall faster as compared to the lighter objects. Aristotle was a ancient Greek philosopher. Then in 16th or 17th century, Galileo did some scientific experiments, and he discovered that two objects, heavier or lighter, if dropped from some height, they fall with the same acceleration, same speed. And he proved this by dropping two spheres, one heavier, one lighter, from the Leaning Tower of Pisa. You must have heard. Even you can perform this activity by dropping a hammer or a feather from the top of your building, and you will find that both the objects will reach the ground simultaneously, provided there is a condition, provided there is no air resistance. This experiment can be done better in vacuum, because we cannot completely ignore the air resistance. That's why a piece of paper or a stone, when they are dropped simultaneously from some height, the piece of paper takes more time to reach on the ground. Reason is air resistance. The air resistance, the paper experiences air resistance. Stone, being smaller, heavier, experiences less air resistance to fall faster. But in vacuum, both will take same time and both will hit the ground simultaneously. Then came Isaac Newton with his universal law of gravitation. Universal law of gravitation is applicable on the earth, in space, and everywhere in the universe. That's why we say universal law of gravitation. According to Newton's universal law of gravitation, the force between two objects is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Two objects, 1 and 2, m1, m2. According to universal law of gravitation, the force between these two objects is directly proportional to product of mass this and inversely proportional to the distance between these two objects, any two objects. So now let's see the universal law of gravitation stated, developed and discovered by Newton. That is in our course. So let's do universal law of gravitation. These are the two objects A and B of mass m1 and m2, and they are placed at a distance that is t. So according to universal law of gravitation, they will attract. Like say these two masses, they will attract, and the force of attraction between them is given by like F. There is a force of attraction. So according to universal law of gravitation, this force between two objects is directly proportional to product of the masses and inversely proportional to the square of the distance between them. The distance d here, m1, m2, product of the masses. And when you combine these two, then you will get here F is equal to capital G m1 m2 by d square. Here this capital G is called universal gravitational constant. I will explain it later. This equation is derived from universal law of gravitation. Right? What is G? Universal gravitational constant. Right? So whenever questions come in the exam that state universal law of gravitation, then you will state the universal law of gravitation and then draw this diagram, right till here. That is universal law of gravitation. Many students only write the statement. No, that is incomplete. Write statement and then these points. Okay. Now let's do a simple derivation. That is the derivation of universal law of gravitation, mathematical derivation. Questions come in the exam, so watch patiently. Here I am drawing two objects, object A and object B. Always the distance is taken from the centers of two objects. Remember, distance from the centers of two objects. And this distance is, say d, x, y, z, you can say anything, d. Mass of object A is m1 and mass of object B is m2. So we can say that consider two objects A and B of masses m1 and m2 lie at a distance d from each other. Let the force of attraction between them be F. F. Then according to universal law of gravitation, here we'll write according to universal law of gravitation, force F between two objects, between two objects is directly proportional to product of their masses. That is, this F is directly proportional to m1 into m2. Let's say equation 1. According to universal law of gravitation, force F between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, and inversely proportional to the square of the distance between them. So we can write here F proportional to 1 by d square, and let's say this is equation 2. Now when we combine these two equations here, combining equation 1 and equation 2, we get F proportional to m1 m2 by d square. Now to equate this equation, we need a constant. So F is equal to capital G m1 m2 by d square. This is the final equation, and here this is the final and very important equation, universal law of gravitation, right? F is equal to capital G m1 m2 by d square. Now what is capital G here? where capital G is a constant of proportionality. And is known as universal gravitational constant. And is known as universal gravitational constant. So now this capital G is very important for this chapter. And the value of capital G was calculated by Henry Cavendish by using a sensitive balance. And its value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Newton meter square per kg square is the SI unit of universal gravitational constant, or capital G. We'll see that here. So SI unit of capital G Newton meter square per kg square, and value of capital G is 6.67 into 10 raised to the power minus 11. So when you write value, you must write unit also with this. Newton meter square per kg square. And this value remains same everywhere in the universe, remember. This value doesn't change. Everywhere, whenever you write this equation and solve numericals, always replace this G with this value, 6.67 into 10 to the power minus 11 Newton meter square per kg square. And this is the derivation part, very important for the exam. They ask you simple question, 3 marks question, derive the universal law of gravitation mathematically. So you will start with the statement and then till here, till this point, right? Step by step, that's quite easy. So that was universal law of gravitation. Now we'll see the force of attraction between different objects, because many students ask questions that if this force is attractive force, then why don't all the objects move towards each other? We see all the objects around us remain stationary. They are not moving towards each other. So the answer is because the gravitational force is very, very weak force. So the acceleration produced in the object is invisible, especially the smaller objects, smaller masses. But if you want to see the acceleration because of gravitational force, then very simple, I will show you. This is the acceleration produced because of the gravitational force of Earth on this object. And remember, this object also exerts the same force on the Earth. but Earth doesn't move towards this object. Again, common question. Many students ask, sir, when the force, remember, these forces are equal and opposite. Here, this object exerts force on this object, F, and this object exerts force on this object. Both the forces are equal and opposite according to Newton's third law of motion. Remember, whether the object is bigger or smaller, the force between the objects will always be equal and opposite. So, this object and the Earth, now generally, it's a general concept. Students think that the Earth exerts larger force on the object, so object moves toward the Earth. No, it's a wrong concept. The force of Earth on this object and the force of this object on the Earth is exactly equal. These forces are equal and opposite. But this force produces acceleration in the object because the mass of this object is very small. So this force is sufficient to produce acceleration in this object, so object starts falling down. And this force is not sufficient to produce an acceleration in the Earth. So the Earth starts moving towards this object. Yes, acceleration is produced in the Earth, but that is not visible. That is very, very small. And so, Earth doesn't seem to move towards the object. Remember, forces are equal and opposite. In gravitation, force between two objects is equal and opposite. Now we'll discuss about the force between the Earth and an object. Let's say a 10 kg object. And the acceleration produced in that object and the Earth. We'll see that. Consider this is the part of the Earth and this is center of the Earth. Mass of the Earth is, let's say, me, and this is the object. So the distance between the object of mass m and the center of the Earth is taken as equal to radius of the Earth, right? This distance is very small because object is closer to the Earth, so smaller distances can be ignored. But when the distance is very big, like suppose object is 800 kilometer away from the Earth at a height of 800 kilometer and 500 kilometer, then we will consider that distance. Then in that case, you will add the radius of the Earth plus height. But in this case, because it's few meters away from the Earth, so this distance can be ignored. So the distance between the center of the Earth and this object is radius of the Earth, which is, I consider, RE. So we know that the force is exerted between these objects. Let's say this force is F. This force is F. Now we can write the equation of force using the universal law of gravitation. So this is equal to F is equal to capital G into mass of the Earth, mass of first object, and then mass of this object, m, divided by a square of the distance, which is radius of the Earth. Like this. So this is the equation of force exerted between an object and the Earth. Now we know that object falls towards the earth. Earth does not move towards the object. There is a reason. We'll discuss that part. And question comes in the exam that explain why does earth not move towards the object while object move. Let's see here. Now, mass of the earth is 6 into 10 to the power 24 kg. Here. And value of G we know, 6.67 into 10 to the power minus 11. And this mass, let's say that this mass is 10 kg. Now put the values, and radius of earth is, so mass of earth is here 6 into 10 to the power 24 kg. And radius of earth is 6400 kilometer, which is equal to 6.4 into 10 to the power 6 meter, because we need SI unit to calculate force in Newton. Now substitute the values. F is equal to here 6.67 into 10 to the power minus 11 into mass of earth is 6 into 10 to the power 24 kg into mass of this object, which is 10 kg, divided by square of this radius of the earth, which is 6.4 into 10 to the power 6 meter square. And when you calculate this, you will get force which is 98 Newton. It's a calculated value. So you can calculate and see it's 98 Newton. So the force between the object and the earth is 98 Newton. Now we know that in the forces and laws of motion chapter, we studied when force is applied, when an unbalanced force is applied on the object accelerates. So force produces acceleration in the object. So this force produces acceleration in this object as well as earth. Object of mass m as well as in the earth. But the acceleration produced in this object is far, far more than the acceleration produced in the earth. Now see that. First of all, according to Newton's third law of motion, as I explained earlier, that the force between earth and this object is equal and opposite. And not only earth and this object, between any two objects, this is valid, that the forces are equal and opposite. For example, so this force, 98 Newton force is exerted on this object of mass 10 kg and 98 Newton force is exerted on the earth due to mass m. Clear? Now we'll see, according to Newton's second law of motion, when force is applied on the object of mass m, acceleration is produced. Now let's see the acceleration produced in mass 10 kg and the acceleration produced in the earth, which has mass 6 into 10 to the power 24 kg. So according to Newton's third law of motion, according to third law of motion, force of object mass m is equal to negative force of object Earth. According to Newton's third law of motion, these forces are equal and opposite. So force exerted by mass m on the Earth is equal to force exerted by Earth on the object of mass m. And these forces are 98 Newton. Now, according to Newton's second law of motion, force of mass m on the Earth is equal to mass of the Earth into acceleration produced in the Earth. And so, acceleration produced in the Earth is equal to force 98 Newton, force divided by mass of the Earth, which is 6 into 10 raised to the power 24, which is equal to 98 divided by 6 into 10 raised to the power 24. Which when you calculate, you will see that is equal to 1.63 into 10 raised to the power minus 23 meter per second square. Right? So this force produces such a small acceleration in the Earth, and acceleration produced in the mass because of the same force, which is 98 divided by, better to write like this, force divided by mass of the object. So acceleration produced in the mass, which is 10 kg, force exerted by the Earth on the mass and mass of the object. That is equal to 98 divided by 10, which is 9.8 meter per second square. Now compare the acceleration produced in the Earth is far smaller than the acceleration produced in the 10 kg object. And remember, this is the acceleration which is produced in all the objects falling around the Earth, closer to the Earth especially. This is common acceleration, and this acceleration is called acceleration due to gravity, that we'll discuss separately. So this was the force between an object and the Earth that we calculated here, which is 98 Newton for 10 kg object. For different objects it would be different, right? But the acceleration produced in the object will remain the same, and the acceleration produced in the Earth will vary, but with very small amounts, right? It always be very small value.